Hey friends, welcome back to the channel and to the 9th episode of Research Papers Summary. Today I'll be covering an ACR 2020 paper, An Instance-Based Learning of Span Representation, a case study through NER. Interpretability of models is extremely important when it comes to applying machine learning to practical applications. This paper shows how instance-based learning can be used to build models that have strong performance results and high interpretability. In this video, I'll first cover the context and contribution of this paper. I will then dive straight into the instance-based span representation model. And lastly, I'll finish up this video by sharing some of the experimental results and analysis. Hope you find this video useful. Let's get to it. If you're new here, my name is Ryan. I'm a first-year PhD student based in London, and on this channel we share and explore actionable insights on different topics in AI research, entrepreneurship and life design, encouraging us to take more actions and live a happier and more intentional life. If these topics are interesting to you, consider subscribing. Neural networks tend to achieve high performance results, but their predictions are usually hard for humans to understand. In order for us to apply machine learning to practical applications, we need to improve the interpretability of these neural networks. In this paper, we focus on using instance-based learning to improve the interpretability of models without sacrificing their performance. Instance-based learning is a machine learning technique that learns the similarities between instances and uses it to predict future unseen instances. The class label of the most similar training instances is assigned to the unseen instance. The reason why this method improves the interpretability of models is because we can trace back to which training instance contribute towards the final prediction. Overall, the main contributions of the paper are as follows. Firstly, the paper claims to be the first to apply instance-based learning to span representations. Secondly, the paper has demonstrated empirically that by using instance-based learning, we are able to build high interpretability models without sacrificing strong performance results. Let's now move on to instance-based span classification model. As the title of the paper suggested, we're using NER task as the case study for evaluating the effectiveness of instance-based learning. The one thing I would like to point out is that instance-based learning here is applied to span representation for NER rather than the traditional token-wise classification such as the BIO tag schema. The two reasons for why we apply instance-based to span representation are because of better performance and interpretability. After all, span classification can naturally deal with inconsistent label prediction as well as nested entities. Let's now take a look at how instance-based span model works. At a high-level overview, the instance-based span model classifies each new unseen span based on similarities between spans. The model does this by using the encoder to map both the entity candidate and the spans in the training set onto the feature vector space and compute the similarities between them in order to get the label distribution. This method is great because it tells us how much each training instance contributes to the final prediction, which improves our ability to explain and understand the logic behind the model's predictions. So how do we train this model? First, let's look at the formula for the neighborhood span probability. In order for us to capture spans that are semantically similar to each other, we need to compute the neighborhood span probability for each span against other spans in the training set. As you can see in the equation, the score numerator computes the similarity between span I and span j, and the entire equation computes how closely each span in the training set is to span I. As you can imagine, the computation of the neighborhood span probability is computationally heavy because you have to do it for every single span in the training set. To reduce this heavy computational cost, we decided to use random sampling instead to select k sentences from the training set. Specifically, we randomly select k sentences for each mini batch at each epoch during training time. Next up, we will use the neighborhood span probability to compute the label of span I using the formula here. The SD'(yi) here means we will sum up the probabilities of neighboring spans that have the same label as span I. Our objective is to minimize the following loss function, the negative log likelihood. And lastly, during inference time, we simply predict the class label with maximal marginal probability as follows. This equation is probably best explained by this portion of figure 1 as you can see here. Let's now move on to the experimental results. The datasets used in this paper are the Cornell 2003 dataset for the flat NER and the Janier dataset for the nested NER. Our baseline model is the classifier-based span model. The only difference between classifier-based and instance-based span model is whether to use the softmax classifier or not. Here are the different results and analysis. As you can see here in table 1, instance-based span model was able to consistently achieve comparable results against classifier-based span model in both GLOV and BERT settings. Next up, we evaluate the effects of different training sizes on the NER performance for both classifier-based and instance-based. We observed that performance for both models gradually decreased when training data decreased. However, both models still have very competitive performance scores. In terms of qualitative analysis, we found that the span feature space learned by instance-based method can be applied to different downstream tasks such as a span retrieval system. Here you can see that the instance-based classifier was able to consistently retrieve the correct type of entities, whereas the classifier-based wasn't able to do so. However, as you can see in the next table, the instance-based span model doesn't perform well with location and organization entities, as it often mixes them up together. We found that most often it is the country or district entities that confuse the model. And lastly, we wanted to find out whether our methodology and results can be replicated in other similar tasks. To do that, we apply our methodology to the Cornell 2000 dataset for syntactic chunking, a task that is very similar to NER but differs in class labels. As you can see here, the instance-based span model was able to achieve competitive F1 scores against the classifier base, showcasing the generalization ability of our methodology. And that's it for today's video. If you like this video, be sure to subscribe as I'll be covering more research paper summary in future videos. In the meantime, feel free to check out other videos on my channel. Thank you for watching. I'll see you guys around next time.